Hello students, in this video we'll prove Stirling's formula. Stirling's formula is an asymptotic result It states that the limit as n goes to infinity of n factorial over n over e to the n root n is equal to the square root of 2 pi, okay? So in this video we're going to prove that this limit exists, and in another video we'll prove that it's equal to root 2 pi, okay? And so the main ingredient in this is that in our notation, what we're going to do is we're going to set, just for context, we're going to write natural log just as an ordinary log in our problem, okay? Just to avoid confusion. And so now here goes the proof. So since log of x is increasing, we know for any j in n, we have the integral from j minus 1 up to j of the log of x dx is less than or equal to the log of j is less than or equal to the integral from j to j plus 1 of the log of x dx. And if I sum from j goes from 1 to n, so summing this relationship, so summing this, we have that the integral from 0 to n of the log of x dx is less than or equal to. Now if I sum logarithms, if I have the log of 1, log of 2, log of 3, all the way up to the log of n, the log of the sum is the log of the factorial. So this is going to be the log of n factorial less than or equal to the integral from 1 to n plus 1 of log of x dx, okay? Now I know an antiderivative log is just x log x minus x, so this tells me what? This inequality over here tells me that n log n minus n less than or equal to log of n factorial less than or equal to n plus 1 log n plus 1 minus n, also because it has an interval, it's an interval of length n as well, okay? So that's good. So that gives me a bound on n factorial in terms of n to the n over e to the power n, basically, a lower bound, okay? So now let's consider the sequence. Let's consider the sequence that we care about. So we're going to consider the sequence dn, and what's dn going to be? It's going to be the log of this thing over here. So it's going to be the log of n factorial. That's the log of the numerator. Then I'm going to have a denominator, which is going to be, I'm going to need an n to the power 1/2, so I'm going to need a minus n plus 1/2 log of n, in the regular log of n, and then a plus n over here, okay? And then what will this correspond to? Of course, this dn corresponds to what? It corresponds to the corresponds just to the logarithm of this thing in my limit over here. So that's the relation we consider, this log of our ratio over here. And I'll look at the difference of dn and dn minus 1. So let's do that. So let's do dn minus dn plus 1, the next further one up. What will that be? So let's see what's going to happen. So I'm going to have an n, and I'm going to have an n plus 1 with a negative sign, so I'm going to get a negative 1. And then what will we have? We'll have an n factorial minus log of n plus 1 factorial. That will give me a log of what? Of 1 over n plus 1. And then we'll have a negative n plus 1/2 log n. And then a positive n plus 3/2 log n plus 1. Okay? So let's see over here. So what I'll do is I will sacrifice one of these log n plus 1s, and that will eliminate one of these things, so that will turn this back into a 1/2 over here. And so what we've just shown is the following. So hence we have this. We have dn minus dn plus 1 is going to be negative 1. And then what's left over is going to be a n plus 1/2 n plus 1, and now what is n plus 1/2? So we can note that n plus 1/2, this is going to be important for us, is really 2n plus 1 over 2, okay? That's what n plus 1/2 is. Good? And then I'm going to have a what? Then I'm going to have an 2n plus 1 over 2 times the log of n plus 1 over n, okay? And so now I'm going to need to use the Taylor expansion of this thing over here. So I'm going to note is I'm going to note that we can check that this is actually equal to what? This is actually equal to -1 plus 2n plus 1. That's the variable I want. I want to say 2n plus 1. And then times 1/2. And then it's going to be the log of 1 plus 1 over 2n plus 1 over 1 minus 1 over 2n plus 1. Okay? And we can check this, because what we'll get a 2n plus 1 plus 2. That's going to be a 2n plus 2 over 2n plus 1. So all the 2n plus 1s are going to cancel out. I'm going to have a 2n plus 2 over 2n plus 1. That gives me the exact same structure as this thing over here. So algebraically, these things are equivalent. And so now what's the key feature of this? The key feature of this is that I'd like to use a what? I'd like to use a Taylor expansion. And so I'm going to recall what the Taylor expansion we want is. So recall that 1/2 natural log of 1 plus x over 1 minus x is equal to x plus x cubed over 3 plus x to the 5th over 5 plus x to the 7 over 7, and so on forever. So that's the Taylor expansion of that function. So if we Taylor expand this difference, what are we going to see? If we Taylor expand this difference, continuing on, what we see is this is going to be equal to, this difference is going to be -1 plus 2n plus 1. And then what? And then I'm going to have a what? We'll have the first term in our Taylor expansion is just going to be a what? A 1 over 2n plus 1. That's my number over there. This, of course, is valid for x less than 1. That certainly is less than 1. Then I'm going to have a what? Then I'm going to have a 1 over 3 times 1 over 2n plus 1 quantity cubed, and so on and so on and so on and so on. Okay? Now the first term, what's going to happen over here? This first term over here is going to cancel out with that and turn all these odd powers to even, and this -1's going to cancel with that first term over there. So really what's going to happen is we have this sum over here. It starts at 1/3, and it's going to be a 1 over 2n plus 1 squared. Then the next term over here is going to be a 1/5, 1 over 2n plus 1 to the 4th power, and so on like that, okay? So we've just shown what? Now all these terms over here are greater than or equal to 0. So this is greater than 0. So what have we just shown over here? We've just shown that dn minus dn plus 1 is greater than 0. So we've just shown this dn sequence is what? This dn sequence is decreasing. So dn is bigger than dn plus 1. So I have a decreasing sequence. This sequence dn is decreasing over here. And then what else can we say? Well, now I can make these terms bigger over here. I can say that dn minus dn plus 1. I can make all these terms bigger over here by replacing all of these, the 1/3, the 1/5, the 1/7, all by 1/3. So this is less than 1/3. And then I have a 1 over 2 to the n plus 1 squared, and 1 over 2 to the plus 1 to the 4th power. That's a geometric progression. So I can sum up that geometric progression. It's going to be a 1 over 2n plus 1 quantity squared over what? Over this thing, the common ratio over here. So 1 minus 1 over 2n plus 1 quantity squared, right? And of course that simplifies just to what? That's just going to simplify. Then I can write this as a 1/3, and then a what? And then a 1 over 2n plus 1 squared minus 1. So that's going to be a 4n squared plus 4n, and then the minus 1's cancel out. So I can pull that 4 out, and I have a 1/12, and then a 1 over n squared plus n over here. And that, by partial fractions, is equal to 1/12, 1 over n minus 1 over n plus 1. Okay? We can just check that immediately. That's immediately obvious just by doing the subtraction over here. And what does that show? If I rearrange this, this says that dn minus 1 over 12n is less than dn plus 1 minus 1 over 12n plus 1. So that says that the sequence dn minus 1 over 12n is increasing. So we've just shown that now. So I have that it's decreasing. So here's one thing that we have. We have this over here. And then we have, so in other words, decreasing sequences are bounded from above. So whatever D1 happens to be or D10 happens to be, so that's going to be the maximum. So D10 is the maximum. So that decreasing that sequence Dn is bounded from above. And so now what I have over here is I have an increasing sequence. So since this sequence is decreasing and this sequence is increasing, I know that 1 over 12n is tending to 0. And this sequence over here is bounded, right, because it's decreasing. So I have a bounded sequence and a sequence that tends to 0. So this sequence over here has to converge. So this implies that the sequence Dn converges to some number c. So we've just proven that this limit over here exists, and in the next video we'll show that that limit, the limit c, is actually going to converge to the square root of 2 pi. Thank you very much.